Okay, good morning students and welcome to today's session. So we will continue ahead with work power energy today. Last time we had discussed about the work done by variable forces, and in particular we had derived the expression for work done by a spring. So that was something important. So let's start with a recap of that and continue ahead from there. Right, so this is work power energy session number 3 for us. As I said, a quick recap of what we had learned last time. So we had seen work done by a variable force is calculated by path integration. And an important example of this, as we discussed, was the work done by spring. So what we had understood is that when we attach a spring to a body like this, if this is the x equal to 0 position where the spring is in natural length, then when the body is at a positive x coordinate, the spring force is negative kx like this. Okay, and similarly, when the spring is in a compressed state, so the body is at a negative x coordinate. You can see that the spring force acting on it is like this. Okay, so as a vector we can define the spring force as minus kx I cap. Where I cap is the unit vector along the length of the spring, and x is such that positive x is the extension and negative x is the compression. Therefore work done by the spring is integration of f dot ds, where here the displacement is along the spring's length. Okay. Yes, okay. So with this in place, the work done by the spring in any general situation becomes minus kx dx integrated from initial position to final position. So we get the final formula that the work done by the spring is minus half k into final x square minus initial x square. So this is something important that we derived last time. We can just make a quick recap of this. We'll discuss more. Okay, so one important part of the application of this is that given this expression, you can understand that if a spring is initially at natural length position, or what we call unstressed, it's not under stress. So x initial is 0 and is either compressed, so x final is minus x, or extended. X final is plus x by x. Then the work done by the spring is negative of half kx square. So this is the work done from natural length to a deformed state. The spring does negative work. Whereas on the other hand, if the spring is initially deformed, okay, that is either x initial is plus x, that is extended, or x initial is minus x, compressed. And finally back to natural length. So x final is 0. Then work done by the spring will be plus half kx square. So this is when you are going from deformed state to natural length. So whenever a spring is taken from natural length to some deformity, the work done by the spring is negative. And whenever the spring is initially in a stress state, either compressed or extended, and from there it's coming back to natural length situation, the spring is doing positive work. So this is an important application of the above formula, the above more general formula, that the work done by the spring is given by this kind of expression in terms of the initial state and the final state. Okay. In this you can see this is the initial state of the spring and this is the final state. Okay. So just remember this formula. Okay, these are obvious applications of this. Okay, next up we come to our first important theorem, and that is the work kinetic energy theorem. Let's understand the statement of this theorem. It says the net work done by all forces acting on a body or a particle equals to the change in its kinetic energy. Okay, where net work done is the algebraic sum of work done by all forces, and kinetic energy, as you know, is defined as half mv square. So the statement of this is that the net work done is equal to the change in kinetic energy, or the net work done is half m into final velocity squared, or you can say final speed square, minus half m into initial speed square. So this is the statement of the work kinetic energy theorem. Okay, so this is one of the two theorems that we are going to discuss, and for application of this theorem only we learn the concept of work done. Okay, so let's look at some important applications of this. So one very simple example, let's start with. So let us say we have this inclined plane. Okay, we'll come back to this. Finish writing down the previous expression. Okay, so let's come back to our example. So we have this inclined plane. This is a rough inclined plane. So coefficient of friction is given to us as 0.5, let us say. Okay. Now a block is released from this position, a 2 kilogram block, and after some time it reaches here, making a displacement of S, let's say. So a block of mass 2 kg is released from rest on a rough inclined plane as shown. So you want to find first of all the work done by each of the forces acting on it through a displacement of, let us say, S equal to 5 meters. So by the time it comes down by 5 meters, the displacement is S. I mean, the displacement is 5 meters and the speed is V. Secondly, we want to find its instantaneous speed, V, at S equal to 5 meters, okay, using work kinetic energy theorem. So just take down the question. We'll discuss the application of it. Take down the question and make the free body diagram of the block to understand what all forces are acting on it. Then we'll come to the first part, the calculation of the work done by each of the forces. Okay, so let us start by understanding the work done by each of the forces. So as you know, the forces acting on the block is something that we've learned in Newton's laws and friction chapter. Will be the weight mg acting vertically downwards. Okay. The normal reaction that the surface will apply, which will be along the normal to the surface. Okay, so therefore this angle here will be the same theta as the inclined plane is making with the horizontal. Okay, and then of course in this case there is also kinetic friction, which will be acting like this, opposing the slipping. So this kinetic friction will be mu n, and as a result of that, that block has an acceleration in this direction. So as it starts with initial velocity 0 at t equal to 0, by the time it reaches somewhere here, some velocity v, some displacement s. Okay, like this. So we can see that the displacement's direction is this. It is down the inclined plane. So it is like this. This is the displacement vector. Okay. So normal reaction will have a magnitude of mg cos theta. So remember m was 2 kg. We take g as 10 meters per second square, and theta is 37 degrees. So this will become 16 newtons. So kinetic friction and mu was 0.5. It become 8 newtons in magnitude. So we will see that work done by mg will become mgs cos 90 minus theta. So you can see that this angle here, this is 90 minus theta. So it will become 20 multiplied by, we wanted a displacement of magnitude 5 meters. So 60 joules. The work done by mg is positive of 60 joules. Okay. Now similarly, if we calculate the work done by the other forces, work done by normal reaction, that will become n into s into cos 90 degrees, because as you can see, normal reaction is perpendicular to the displacement. So that is 0. And the work done by friction will be kinetic friction into s into cos 180 degrees. So that is negative of kinetic friction into displacement. So we had seen the kinetic friction was 16 newtons. Sorry, the kinetic friction was 8 newtons, my mistake. So minus 40 joules. This is the work done by the friction. Okay. So these are the various quantities. Okay, so just make a note of this and then start the second part. We have to calculate the speed of the block by using work kinetic energy theorem. Okay, Krupa, we'll just check the answer you've calculated. So second part, we can see that net work done should be equal to change in kinetic energy. Okay. So our initial speed was 0. So that means our initial kinetic energy is 0. Final speed we have to find out. So the net work done should be the work done by the weight, the work done by the normal reaction plus the work done by friction. This should be equal to half mv square. Okay. So this is what our statement is becoming here. Yeah, square root of 20 is the correct answer. So work done by mg we just saw is 60 joules. Work done by normal reaction was 0. Work done by friction was minus 40 joules. So this should be equal to half into m, which was 2 into v square. So as you can see, v square is equal to 20. So v is equal to root 20, or say v is equal to 2 root 5 meters per second. Okay. Now we'll also verify this by another method, but first you can make a note of this. So if you approximate this, it will come out to be about 4.47 meters per second. So Krupa, Varun and Rahil, your answers are correct. Okay, now in this case we can also verify this by simple kinematics. Okay, we can also use, because it's a uniformly accelerated situation, no? So you can also use this. See that the acceleration is g sine theta minus mu g cos theta. So that is, so the acceleration is 2 meters per second square. So if you're starting from rest through a displacement of s, v square will be 2as. So for s equal to 5 meters, so v will become square root of 20. So you can see that this is verified from kinematics. Okay. Okay, now next let's look at a more tricky kind of situation. So what we are having now is this kind of a curved incline. But however, this is a smooth surface this time. Now a particle is released from the top point A from rest, and then by the time it comes here to the bottom of this curve, it has some speed v. So a particle of mass m, let us say, is released from rest at the point A, at the top of a smooth curved surface as shown. Find work done by forces acting on it and that is from A to B, and secondly find out the speed v at the point B. So for doing these parts, given the mass is 5 kilograms, g is equal to 10 meters per second square, and h is equal to say 10 meters, and d is equal to 20 meters. So this information is given to us. Now, while doing this question, we have to be a little bit careful about definition of work done and how to apply work done for different kind of forces. Okay. Remember, this time it's a smooth surface, so there are only two forces acting on it: normal reaction and weight. But we have to be a little bit careful about what method we'll use for calculation of work done for each of the two forces, weight and normal reaction. Okay, so let's understand this like this, that as the object is coming down this curved surface, at different points of time, if you compare, okay, the forces acting on it, you'll realize one thing: the weight is a force which does not change. It's a constant force. Its direction and magnitude always remain the same, which is vertically downwards. So this is the first thing we understand, that mg is a constant force. It's always vertically downwards, okay, and of magnitude. So the mass of the particle was, yeah, Rahil, I'll give you time to copy the question, don't worry. First understand it, okay. So mass of the particle was 5 kg. So the magnitude of the gravitational force is 15 newtons, okay. But when it comes to normal reaction, okay, so I'll give you time to copy, don't worry. First note down this point. Now the normal reaction, on the other hand, what it does, it's a variable force, okay. So it is always changing direction. It's like this over here, like this over here, a little bit more like this over here. So the normal reaction keeps changing direction such that it is always tangential. That means if you draw a tangent at the point on the curve, it is perpendicular to the tangent. It's normal in direction like this. The other point here that we want to note down is that normal reaction N is a variable force such that its direction is always perpendicular to the tangent to the surface at the point of contact. Okay. So because it's a variable force, so the work done will be calculated by integration method. Okay. And because this is a constant force, mg is a constant force, so the work done will be calculated by dot product method. By this method, okay. No, the tangent is not the x-axis, but a tangent to the curve is this dotted red line that we've drawn everywhere, okay. So at the point of the curve ना, जो आपने calculus में सीखा है, if you take a small section of the curve and just extend it, that becomes the tangent, like that. Is it clear, Sarvesh? अरे बेटा एक्स एक्सिस तो ये है, एक्स एक्सिस से क्या मतलब अपने को, वेयर आई एम यूजिंग द एक्स एक्सिस एनीवेयर. एक्स एक्सिस इज जनरली टेकन एज हॉरिजॉन्टल एंड वाई एक्सिस इज टेकन एज वर्टिकल, बट उससे अपने को मतलब ही नहीं है यहाँ पे. Okay. All right. So just note down up to this point first. Then we'll discuss more. Okay. So finish writing down the question. Those who haven't finished that, and then note down these 2 points. Then we'll discuss more. Okay. So finished with the question. Rahil, you have finished writing down the question. Okay. So now make a note of these 2 points here about the normal reaction and about the weight. There are two forces acting only, which are normal reaction and weight. So this is going to be mg's dot product with displacement. Okay, so let's come to the calculation of the first part now. So for work done by the weight, we are going to use the dot product method. So when you look at the situation here, it's going from this position A to this position B. Now during that time, the displacement vector is which one? The displacement vector is the straight line joining the initial with the final position. So ये हो गया displacement. So in fact, if you see the interesting thing, we don't know anything about the displacement. We only know that, and this is the force mg is acting vertically down. However, the other thing we know is that if we drop this perpendicular from here onto the horizontal, we know this h and we know this b. And you can see in the diagram that the angle between the displacement and this, if this is theta, you can see that this will become mgs cos theta. Now in the diagram you can see that s cos theta in this triangle is nothing but h. So that's what helps us find out the work done by mg. It becomes mgh. Now it was given to us that m was 5 kg, g is 10 meters per second square, and this height was, I think, 10 meters, if I'm not mistaken. So this will become plus 500 joules. Okay, so this is how we calculate the work done by the gravitational force. Okay. Yeah, h was 10 meters and d was 20 meters. You just make a note of this next. Yes, we can find, but उसकी जरूरत ही नहीं है ना बेटा. What we need to find, see, is s cos theta. Na? We can find s. Obviously, s is square root of h square plus d square. But then we'll also have to substitute cos theta. Na? So cos theta will be how much? H upon square root of h square plus d square. So ultimately, we will end up calculating s cos theta as h only. Na? This is what we have to substitute here. Is it clear, Krupa? Okay. So that is why I did not calculate the hypotenuse separately, because it's not required only. Okay. Okay, now let's come to the work done by the normal reaction. Okay. So this is a variable force. So we have to calculate work done by integration of normal reaction over displacement. Now this is where it becomes very interesting, that there is actually no way to calculate normal reaction at a given point. Okay, because it's acting in an arbitrary kind of manner. But the interesting thing is, because normal reaction is always acting perpendicular to the tangent. Okay. So as we had discussed, at any point of time, the direction of normal reaction वो कैसा है, it is perpendicular to the tangent drawn at that point. So it is perpendicular to the tangent. Now if we take a differential displacement of the particle at a given point of time, small displacement ds, उसका direction क्या होगा? It will be along the tangent. So at any instant, the differential displacement ds vector will be like this. Okay. Similarly, by the time the particle has moved here, the direction of normal reaction has changed, but then the tangent is still perpendicular to it. So from this point, the displacement will be along this direction. It is a very small amount of displacement that will be in this direction. From point to point, the direction of displacement is also changing, the differential displacement, according to the tangent of the curve, how that is changing. And the direction of normal reaction is also accordingly changing. So what is happening here is normal reaction's direction is perpendicular to the tangent to the surface at any point, and a differential displacement is along the tangent at a point. So therefore, this normal reaction force is perpendicular to the differential displacement always. So n dot ds is 0. So work done by normal reaction, which is integration n dot ds, becomes 0. So this is a very important little application over here, how the work done by normal reaction is becoming 0. Okay, just make a note of this quickly, people. And then you can calculate the final part. Okay, so finally from this, what we are seeing is for the second part, we'll apply this theorem that net work done is change in kinetic energy. So work done by mg plus work done by normal reaction should be half mv square. So work done by mg was mgh. Work done by normal reaction was 0. So we get the very interesting result that v is square root of 2gh, just like a free fall through a height of h. Even though this is not a free fall, okay, the path of the particle is a curved path, but that is what the speed is coming out to be. Okay, so in this case, v is 10 root 2 or approximately 14.1 meters per second. Yes, that's correct. And Varun. Okay. So now you see the importance of the work energy theorem here, the work kinetic energy theorem, that we cannot calculate this by kinematics because the acceleration is variable. So it will become a very complicated process, and we don't know the equation of the curve and all that. So it's not going to be possible to calculate the speed using kinematics. But using work kinetic energy theorem is quite easy, really. It's an easy one-line solution. So it is specifically for these type of problems that we use work kinetic energy theorem. Okay, where kinematics and acceleration is not going to be easy to calculate, or sometimes not going to be possible only. Okay. So वैसे situations जहाँ पे it is not possible for us to calculate acceleration, or even if we can calculate, the kinematics part is going to be very complicated. There we tend to use work energy concept. Okay. So let us look at another example next. This time we now have a spring mass system. So we'll take the example of this. So a block of mass, let us say m equal to 5 kg, attached to a spring of spring constant, let us say 2 newtons per centimeter, okay, is initially held at rest with the spring extended by x equal to 4 centimeters. by application of a force F external acting horizontally. Okay. So first part is find how much the external force is. Okay. That's very simple. Now second, if the force is suddenly withdrawn means it stops acting, then find the speed of the block at the instant when the spring returns to natural length position. Okay, so we remove this force suddenly. So as a result, what will happen? The moment this force goes away, so right now what was happening? This force was balanced by spring force, okay, and the acceleration was zero. But the moment we withdraw this force, now what will happen is that this will create a sharp acceleration in this direction. Okay. So what we want to find out, and it will start from rest. Okay. What we want to find out in the second part is by the time the spring is back to the natural length position, what is the speed of the block? And this is back to natural length or x is equal to 0. Here it is at an extended state. So just work this out quickly. Okay, so what is the answer to the first part? The spring force is how much? Yeah, Varun, I'll come to the speed. Okay, first let's come to the first part. So initially what is happening, you can see the diagram. Kx will have to be balanced with the external force so that the acceleration is zero, no, initially. And K is 2 newtons per centimeter and X was 4 centimeters. So that means the external force which balances Kx will be equal to 8 newtons. This is the answer to the first part. You have to apply a force of 8 newtons. Now the second part, once this force is withdrawn, okay, this is the initial state. This kind of force is acting, and this is what we want to find out when this is back to natural language. So we can see that on the block only one of the forces is doing work, because normal reaction and mg are acting perpendicular to the displacement. It is only spring force that is doing work. Okay. So only spring force is doing work on the block. Work done by mg is zero. Work done by normal reaction is zero. Okay. So using this, we'll say that work done by spring is equal to change in kinetic energy, net work done. So that will become half k into, or minus half k into this, is equal to half mv square. Because remember, work done by spring was given by this formula, minus half k into x final square minus x initial square. So we'll have this formula that half mv square is equal to half kx square. So v will become x into square root of k by m. Now when we are substituting here, we must substitute in SI units. So v will become, now initial x was how much? 4 centimeters. So 4 into 10 raised power minus 2. Okay. K was how much now? 2 newtons per centimeter. So that is 200 newtons per meter. So this is the value we'll substitute. And m was 5 kg. M was 5 kg? Yes. we have to substitute everything in SI unit. Okay, so K has to be substituted as 200, but X has to be substituted as 4 centimeters. So that's 4 into 10 raised to minus 2 meters. So this is 8 root 10 centimeters per second. Okay, so hope this is clear. Now let's move on to the next section of work energy. So next we will look at a very important definition: conservative force, and the opposite of that, non-conservative force. This is going to be something very significant and very important for us. So let's understand. So we have defined work done by a force in general as F dot ds integration from initial to final. This is the general definition of work done. Okay. It is path integration of force over displacement. Now we have also specifically seen that, of course, if the force is constant, then this work done becomes more specific. It becomes F dot S. But that's only if the force is constant. Whereas if the force is variable, then we stick to the general definition of work done. Now, if the work done by the general definition only comes out to be in such a way that it is independent of the path, but only depends on the position, initial and final. So इसका मतलब क्या हुआ that if we take the body via any path of choice from initial to final, the work done is the same. That means it is independent of path, but it only depends where my initial position is and where my final position is. Then it is called the conservative force. Okay. So for example, if I take a body from this initial position to this final position by one path like this, let's say this is path 1, and during that I'm calculating the work done by some force acting on it. So as the body is moving, the force need not be constant, so force can be variable. And then I'm repeating the same operation by another path. See, that path is like this, and during that path the force is again varying like this. Okay. But if the work done in both these paths comes out to be the same, because I'm going from the same position I to the same position F, and like that the work done in any other path, any arbitrary path will also be the same. So whether I take this path or this path or this path or any other path, if the work done is every time going to be the same, because it does not depend on path, it only depends on where the initial position is and where the final position, then the force is called conservative. Okay. So if the work done by a force F from a certain initial position to a final position is path independent. Okay. That means it is identical for all possible paths from the same initial position to the same final position. Then the force F is what we call a conservative force. Okay. So in other words, conservative forces are ones whose work done is path independent. So by definition, conservative force is one where the work done is what we call path independent. Okay. So that means the work done does not depend on path and only depends on initial and final positions. So make a note of the definition, then we'll discuss with example. Okay, so let us understand this with some examples. Any constant force, okay, work done F dot S is path independent for it because it only depends on displacement. Therefore, any constant force is conservative, first of all. Okay. So just now, for example, we had seen that if we calculate the work done by gravity from A to B, work done by mg from A to B was mgh. Okay. Now instead of this path, if we take another path which is a straight line, okay, but between the same position A, between the same position here and here, so the displacement is the same in both the cases, okay, but the paths are different. You can see the work done is same in both the cases or in any other path. This is independent of path because it's the same in this also, is the same in this also. The paths are different, you can see. So when we consider work done by gravitational force, it has to be a conservative force because gravitational force for us comes in this category. It's a constant force at the surface of the earth. So this is our first example of conservative force. Okay, now next example we'll see of a conservative force is the spring force. That is conservative. because we have seen that the work done by spring force, which comes from integrating spring force with respect to displacement, is ultimately given by the formula this. Okay, so when you consider this formula, it only depends on x initial and x final. The work done depends only on final position xf, because k is of course a constant, and initial position x initial. So therefore it is path independent. So that implies that spring force is conservative. Okay. So for example, if a spring initially at x equal to 0 is extended to x equal to plus x naught, the work done by the spring in that process is minus half kx naught square. Okay. Now next, suppose the same spring initially at x equal to 0 is first compressed to x equal to minus x naught by 2, and then extended to x equal to plus x naught. Okay, the work done will still be equal to this. Okay, so this will still be the final position, and this will still be the initial position. So still, okay, so this will be the same as this, even though the path is different. Okay. In one case, we are directly taking the spring from natural length to an extension. In the other case, we are first compressing it and then we are taking it to the extension. But in both cases, the work done by the spring is the same. So it shows that it is conservative. It is independent of path. Okay. So here you can see that two different paths from initial position of 0. Okay. But same work done by the spring because it is conservative in nature. Okay, so hope this example is clear to all of you and you understood why the work done by the spring is independent of path. It basically comes from this derivation. The way we've derived that formula for work done is minus half k into final position square minus initial position square. So it clearly shows that it only depends on these two things, x final and x initial. So it is independent of the path. Yeah, that's what I'm doing, Sarvesh. I'm explaining the last thing again. So if you take the spring from natural length to a compression first, but then from the compression again to the extension of plus x naught. So according to the formula, आपका initial position से final position, what is the work done? It is this much only, na, minus half k x naught square, which is the same as you would have got if you took it directly from 0 to plus x naught. So two different paths. You can see the work done ultimately depends only on x initial and x final, and therefore it is the same. So that means it is conservative by nature. Is it clear, Sarvesh? Okay. So one final thing about conservative forces. So this is very important. Okay. Since work done by a conservative force is path independent, okay, therefore the work done in what we call a round trip must be zero. So round trip का मतलब क्या है? It is a path such that the particle or body comes back to the initial position. Okay, after completing a round trip or a closed loop. Okay. So this is an important property of conservative force. Okay. So for any conservative force, work done in a closed loop or round trip must be equal to zero. Yeah, because the final position is equal to initial position and it depends only on the position. Path independent means it depends only on position. So if final position and initial position are same, the work done must be zero. Okay, so let us understand this with an example. So supposing we have this situation that we have an inclined plane like this, and what we do is we place a body initially at A. From here it slides down to this position B. Okay, and then from B we push it along a horizontal surface to this position C here. Okay. And then from C we lift it back to the position A, where this height is h. Okay. So for example, a block of mass m initially at the position A. Okay. So it first slides down to B. Okay. Then it is pushed horizontally to C. And then finally it is lifted from C to A again. Okay. So you can see that it is undergoing what we call a round trip, A to B to C to back to A. So it's a round trip. Okay. So if we calculate the total work done by gravity, okay, the gravitational force, okay, in the round trip, you'll see that the total work done will be the work done by gravity from A to B plus the work done from B to C plus the work done from C to A. So when you calculate, you can see that this will be plus mgh, this will be 0, this will be minus mgh. So the net work done is 0. So you can see that work done by mg in the round trip is equal to 0 because it is a conservative force. अरे बेटा C2A आपका डिस्प्लेसमेंट क्या है? C2A, the displacement vector is this, ना? The magnitude h है. And what is the direction of mg? It's acting downwards. So what will be the work done? होगा कि नहीं? Okay, so hope all of you have understood this example. So with this, we will conclude today's session here today. Um Next time we will understand the definition of non-conservative forces, and basically we'll see that it is just the opposite of conservative force. That means if the work done depends on the path, then it is a non-conservative force, or if the work done in a round trip is not equal to zero, then it is a non-conservative force. So far from all the examples of force that we have studied, the only non-conservative force we will see is kinetic friction. We'll understand through examples that if you take a body on a round trip, the work done by kinetic friction acting on it will be a non-zero quantity. It will be negative. For example, on a horizontal surface, you slide a particle on a circular path, bringing it back to where it started from. The total work done by kinetic friction will be a negative quantity. It will not be zero. Okay, so that is an easy way to understand why kinetic friction is an example of a non-conservative force. Okay, so any force whose work done in a round trip is not equal to zero, or where the work done is dependent on the path, that is called a non-conservative force. And from there we will understand the next thing, which is the potential energy for a system, and from that the work energy theorem. So very important part of work energy chapter coming up in the next lecture. So do a bit of pre-reading before the next lecture about conservative and non-conservative forces and about potential energy, because that is what we'll discuss in the next session. Okay, that's it for today's session, people. Wish you all the best.